Good morning, everyone. We are going to talk about sand casting. Sand casting uses a mold made of silica sand, which is mixed with a binder such as clay and water. This type of mold can only be used once, because it needs to be destroyed and disposed of after removing the casting. In terms of process complexity, sand casting is considered low to medium. The fundamental process is simple and easy to understand, and it requires less sophisticated equipment compared to other casting methods. Overall, it is one of the most basic and widely used casting processes due to its simplicity and cost-effectiveness. Next, let's look at the process sequence of sand casting. The first step is pattern making. In this step, a model or pattern of the part is created. The second step is mold making. Sand is packed around the pattern in a flask to form the mold cavity. Then comes coring. Sand cores are placed to form any internal passages if needed. After that, we move to closing, where the coping and drag halves of the mold are clamped together. The next step is pouring. Molten metal is poured into the mold through a sprue. Then comes cooling, where the metal is allowed to solidify inside the mold. After the metal has cooled, we proceed to shake out. In this step, the sand mold is broken away to retrieve the raw castings. Finally, we have cleaning. Gates, risers, and any remaining surface sand are removed to finish the castings. Now, let's talk about the surface finish, production volume, and part size of sand castings. The surface finish of sand castings is relatively rough, because the texture of the final product replicates the granular structure of the sand. In fact, it is considered the roughest among the three casting processes. When it comes to production volume, sand casting is most suitable for low-volume production. It is ideal for prototyping, one-off pieces, and small batches, mainly because of its low tooling cost and flexibility. Lastly, in terms of part size, sand casting can produce an extremely wide range of components. It is capable of making some of the largest and heaviest castings, ranging from just a few ounces to hundreds of tons. Next, let's look at the cost and applications of sand casting. The molding cost is low because the patterns are inexpensive, but the cost per part becomes higher at large volumes since the process is labor-intensive compared to automated methods like die casting. Sand casting is used in many industries, such as automotive for engine blocks and cylinder heads, heavy machinery for pump housings and large gears, aerospace for engine mounts and landing gear, and even in infrastructure and art for pipe fittings and metal sculptures. Now, let's move on to die casting. The mold is made from steel or alloy, making it durable and reusable for thousands of cycles, but also expensive to produce. This process requires high precision and automation, with special machines, skilled operators, and careful temperature and pressure control. Die casting produces a very smooth surface with tight tolerances, so no extra machining or polishing is usually needed. It's great for decorative or precision parts. It is ideal for mass production due to fast cycle times and consistent quality, but not suitable for low-volume production because of the high tooling costs. Next, let's look at the part size, cost, and applications of die casting. Die casting is best for small to medium-sized parts. Larger parts need heavy machines, which increases the cost. The mold cost is high due to expensive tooling, but the per-part cost is very low in large-scale production, so efficiency improves with higher volume. It is widely used in the automotive industry for engine covers and gearbox housings, in electronics for laptop frames and phone casings, and in industrial machinery and aerospace for lightweight precision components. Now, let's look at the process sequence of die casting. First, the mold is preheated and a release agent is applied to prevent sticking. Next, the metal, such as aluminum, zinc, or magnesium, is melted. Then, the molten metal is injected into the mold under high pressure, which can reach up to 200 megapascals. The metal solidifies quickly under pressure, and once it cools, the mold opens and the finished part is ejected. Finally, the excess metal is trimmed, and the surface is cleaned or finished as needed. Now, let's move on to investment casting. This process produces a very smooth surface and can create fine details and accurate shapes. For the mold type, it uses a wax pattern coated with ceramic material. The ceramic mold is temporary and must be broken after casting to remove the finished part. In terms of process complexity, investment casting is more complex than sand casting and die casting. It involves several steps, including wax pattern making, coating, drying, melting the wax, and casting the metal. Now, let's look at the process steps of investment casting. First, wax is injected into a mold to form the pattern. Then, several wax patterns are assembled into a tree shape. Next, the wax tree is coated with ceramic layers to make a strong shell. After that, the wax is melted out by heating, leaving a hollow ceramic mold. Molten metal is poured in, and once it cools, the ceramic shell is broken to remove the castings. Finally, the parts are cut off, cleaned, and ready for use. Now, let's look at the production volume, cost, and applications of investment casting. It is suitable for low to medium production and not ideal for mass production since the process takes time. It's best for small to medium parts, not very large ones. The cost is medium to high because of the complex processes in ceramic materials, but it produces high quality and precise parts. Applications include aerospace components, jewelry and art pieces, medical tools, and industrial machinery parts. Conclusion: each casting process has its own advantages. Sand casting is flexible and low cost, great for large parts and small batches. Die casting is fast and precise, best for mass production. Investment casting offers excellent surface finish and accuracy for complex shapes. The best method depends on the product's design, size, cost, and production needs.